All right. Make sure. Okay. All right. So this is going to be part B of homework process dynamics homework 3. Homework 3. So this is supposed to be the Python script part, but I think it always helps to write out a diagram if you're working with a unique system. So I'll make this full screen. I just want to show that what I'm writing out is actually what's portrayed on here. Okay, so a column has condense. Okay, I read that incorrectly first. So we have a distillation column. Here's our feed. Again, I'll enlarge it in a second. Trace stages between the condenser and the feed stage. So we have 2 rectifying stages. And 3 between the feed stage and the reboiler. 2, 3. So let's go ahead and number these. We'll do 0, 1, 2, 3, 4, 5, 6, 7. Sorry, I'm just writing this out. You can see in the little box up in the corner that I am. All right. Feed flow F1 Z equals 0.4. F equals 1.5. Relative volatility is assumed to be constant at 2, which means that we're assuming that the heat of vaporization for both of them are close enough to where the difference is 0. So that's going to be our alpha term, and that's going to be equal to 2. Flows via overflow at a rate of, okay. So L equals 0 times H minus H naught, which is again hold up minus hold up naught minus 1.5. Hold up naught is 0.5 for all stages. This also means that this 1.0 number is our W. of the reboiler, which we can actually note. We'll just notate that kind of as a matrices. So that would be our very last one, which would be -1. It's going to be 1. The trays in the reboiler are filled throughout, initially with the feed liquid at greater than. Okay, so that just means that in our very initial state, we're not dealing with H naught equaling just H naught, which would mean that we have no liquid flow rate. We're actually a little bit above, so there's actually some kind of liquid flow rate going on. So H initial, we'll just call that HI equals H naught times 1.05. The initial condenser holdup is set to provide a flow half of the feed at the refill. Okay, I see. Half of the condenser. So, shoot, I would have to go back and check this, but I don't know if that means. So, we're saying there's a holdup that would give us a flow up at the condenser the L naught V1. So it's saying, what did it say? That we have an initial holdup, so H, that would give us a flow that's half of our feed, which would be 0.75 moles per second. I don't know if that means that it would give us a liquid flow that would be half of our feed, or if it means that it would give us a total liquid and distillate flow rate that would equal 0.75. I would have to go back and double check that. Okay, and then no matter what, our reflux ratio, which is going to be L0 over D, is going to equal 2. All right, so let me go back and double check that information. We have this written out, so that's going to help us understand things conceptually. And while I'm writing out the Python code, I will be looking back down at this. Let me see if I have what we're going to work with pulled up. Yeah, so I have that. I already wrote out. I wrote out the problem statement, our imports, and then I just put what the what our parameters are. So I haven't actually done any equations or anything regarding matrices. It's just basically what we've written out is what we've already talked about. So we'll come back to this. All right, let me bring these back up to the front. So this is going to be Part B. Yeah, or this is the coding portion for Part B. We went ahead and wrote everything out. I don't know. We just did this. This is what I'm using as a reference. Yeah, now we'll actually translate it to code. I went ahead and just put down what our parameters are, or our constants, which was all given from the, what's it called? The problem statement. So where we'll want to go from here is we'll want to actually make a matrices for these. So we'll have how many total? So 1, 2, 3, 4, 5, 6, 7, 8. So we need a matrices of 8 by 1, 8 column, 1 row. And each of these is just going to hold what would be our holdup values and then our liquid mole fractions. So we know from the problem statement that the holdup value would be the same in stage 1, 2, 4, 5, and 6. Because we know that those are just regular stages, so those are going to be 0.5. We'll give the feed stage its own, which is going to be number 3, because that's going to have feed go directly into it. And then reboiler and condenser are their own deal, as said in the problem statement. So we're going to have np.r. I'm going to concatenate these guys. So we'll have condenser up. I don't think that needs to be in brackets. Then we have, so we're starting at the condenser. Then we have 2 stages of 2 state. Yeah, we have. Is it np.full? Yeah. So then fill any value. So we want 2. They need to be filled with stage holdup. Come on. We have our feed stage. And we have this again. It's going to be 1, 2, 3 stages for our stripping section and reboiler. Basic. So that's our holdup. Or that's holdup 0. So hold up 0. And then our initial holdup we'll just have that be holdup I. It's going to be hold up 0 times, what do we say? 1.5? 1.05. That one correctly? Okay. And then finally, we just need our liquid mole fractions. So that's going to be dot full. And that's going to be, we want as many spaces as our holdup I or not, I guess it doesn't matter. And we want it to be filled with values of Z. Is that what it's saying? All right. So 1, 2, 3, 4, 5, 6, 7, 8. Yep. Yeah, we're just going to have them start out with our feed hold up initially. So we'll have this be our X naughts. Those will change. Okay, now we need our ramp function because what is it saying? Condenser set to provide a flow. The feed is ramp from 0 to half the distillate flow. Okay, yeah. So we need a ramp function. So we'll do ramp function. We'll need T, A, and B. Got it. So basically, it's ramp from, so anything below 0, the ramp is just going to be 0. And then those will be inputted as A and B. So if A is then 0, return 0. If B is greater than 1, else we'll do E minus A divided by A minus B. All right, so we'll be right back. We'll check up on this. Come on. There we go. There we go. You made a mistake. This is supposed to be B minus A. Okay, so let's plot this out just to kind of see what's going on. So fig equals make subplots. We'll have y equal to ramp function. We'll do maintain. Let's do an example of what's actually going to happen. So we'll do T 50 to 100. We'll do 300. Space. Zero to 300, and we'll do 30 spaces. Scatter. X, Y equals Y, node, ones. Okay, so we got a syntax error. We'll be right back. Okay. We figured out where we messed up. First of all, this L should not be. I mean, I guess it could, but we need to do it like this. Also, I totally messed up the if statements. It needs to be if t is greater than whatever value of b we put in, then it's just going to return y is equal to 1 as a straight line for all values of t after that. If t is less than a, then everything before that needs to equal to 0. So then the only time that it's not 0 or 1 is everything in between b and a, whenever t is in between b and a, and that's going to be this slope that we have right here that goes from 0 to 1. So we need to make our subplots. I messed up on the syntax of this. This needs to be up here. So it needs to be iterative. So this shouldn't be capital. And then it needs to go multiple times, not just once. I messed up on that part. Is that it? Yes. Okay. So as you can see, every 0 up until t finally gets to 50, and then it ramps all the way up to 1. So you can multiply the ramp function by anything to like kind of scale it up. You can also shift it up if you want to add 1, or shift it down if you want to add 1 from, or any value from the function. That's it. Now we'll go on to actually defining our values for our differential equations. So we need to get some kind of function for our differential equations of our molar flow rate and our what's it called? Liquid composition of our more volatile compound. I can't think. So those are just going to be our differential equations. Those are our differential equations. Diffees. And then we'll use solve IVP after that to actually solve for those differential equations. So integrate them, and we get actual values over a span of x values, which we can then plot. But first we have to solve for this. Right. One thing that I did want to jump back to is we do have to define, we do have to set specifically what the be the holdup of our condenser would be. So that would just be the 0 part in our matrix. And that would be, you would basically just solve for what the holdup would be. If you replace L with R plus 1 times D, which if you look back at the transport 2 video, or not transport 2, but separations part 2 video, you can see how that's derived. And you solve backwards from L equals W times blah, 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 and then you get your holdup from that. So that's going to be, first you would look at L and you would divide that by W. So it would be L divided by W. All that is going to be raised to 2 divided by 3, which is the opposite of 3 over 2. And then times hold up 0 space 0, which would actually just be condenser hold up. Like we said, is going to be R plus 1 times E. And we have an extra one, I think. Let's just bracket all that to be safe. Okay. So let's go back to what our differential function is going to be. So this is going to be, we'll need time, because, I mean, this is process dynamics. Everything changes with time. And then we have our two different differential equations that we'll need, which are going to be dx, which we'll have to pull from dm, or d parentheses mx, and then just dm. Then we need our reflex ratio function. So first off, r is just going to be reflex ratio as a function of temperature. D is going to be, so as we said, D is actually going to ramp up. We want it to be half of what our feed is, but that's going to ramp up after 100. So that's going to ramp all the way up to half of our feed in 100 sections, and it's going to take from 50 to 100 to get there. So we're going to do ramp function T 50, 100, F divided by 2. For DMs, so those are going to be just an array zeros. It's going to be like, oh shoot, we need to set what our DDT is. So that's going to be do M and then X. That's going to be dot T dot split. Can't spell. DDT and 2. We're going to need an array of zeros that look just like the same size of our molar flow rates. And X. With parentheses, it's going to be the same thing. Boy. And then our vapor flow rates are going to be the same deal. Right. All right. I forgot to include our vapor mole fraction. So that's going to be obtained through that alpha equation. We derived that back in separations homework 2. But it's very useful because, or it's very useful for finding y, because since we're saying that alpha is constant, we don't have to worry about that changing at all with temperature. And that's going to be 1 minus x plus alpha times x. All right. Now we need our liquid flow rate, and we can get this with our Weir equation. But we're only going to have a liquid flow rate whenever the holdup, is that what we called it? The holdup of the current stage is greater than the holdup knot, which is again the holdup where it's at that height, but you don't actually have anything flowing over. So we need np.Weir, and that's greater than, what do we have? Holdup 0. Need anything in the X array, and then we need, oh, it would just be the Weir equation. So W times minus hold raised to 1.5. Okay, I think I inserted that correctly. Now that we have, and this is in the rectifying, or no, this would be any stage so long as you input the right M. Then in our rectifying stage, we have vapor flow rate, which is Yeah, that would be the mass balance. So it would be L plus distillate. L from our distillate is going to equal SV rec where do we go from here?